Hi, my name is Kendall, and I will be doing the project, my protein project, the alpha epithelial sodium channel, and my mutation, which is cysteine 479, replaced by arginine. The normal function of this protein is that in a normal structural function, sodium is taken up by the chloride cotransporter or the epithelial sodium channel. I chose this category because the mutation of the transporter is that to be found on the sodium channel. This protein could be this protein typically could be found in the renal tubes of the kidneys, and when the protein becomes more active, a quantification of mature cleavaged alpha epithelial sodium channel cells are in the membrane. Or when it becomes less active. When it becomes more active, the trypsin that increases more probability of it being opened. When the protein gains new function is when any of the amino acids that is found in the alpha subunit of the protein, it is more likely, like any of the amino acids, it is more likely to be, there's likely to gain a new function. So this is my protein, right on this protein, or this part of the protein. This is the normal structure of the protein. This is the alpha subunit, the beta subunit, and the gamma subunit. This is the protein at a aerial view. This is the actual epithelial sodium channel that is found. This is the alpha subunit, like the beta subunit, and the gamma subunit. This is where the protein occurs, or this is where the mutation occurs of the cysteine, of the replacement of cysteine with arginine. Right, these two dots right here are the previous little mutations, and all around this structure or this mutation changes the way sodium channels are reabsorbed and favors the potassium reabsorption into the lumen. So the main functional groups that are found in the original amino acid are sulfur hydrogroups. The cysteine is found to be a hydrophobic amino acid and is polar compared to other sizes of the amino acids. Cysteine is found to be smaller than other amino acids. Though cysteine is a polar molecule, its side chains are found to be hydrophobic, which means that the different types of bonds that can be formed are those sulfide bridges, that the ones that are typically found in the more normal epithelial sodium channel. Because of the hydrophobic nature of the R group, cysteine is more likely to keep polar molecules reabsorbing at a rapid pace. But the mu mutation which is the replacement of cysteine with arginine. Arginine is found to have both polar and hydrophilic side chains. Compared to the fact that cysteine is hydrophobic, arginine is more likely to be in larger size. Because arginine is a polar side chain and hydrophilic, it is more likely to form bonds like hydrogen bonds. Also, because of its empathetic nature, arginine is likely to have both hydrophilic and hydrophobic parts. The mutation that causes the C479R change causes increased intrinsic channel activity. On the physical level, the mutation causes a condition in which somebody, usually little children, develops Little syndrome, which shows that there is an increased sodium reabsorptions in the collecting tubules of the kidneys, which would cause the children to develop metabolic alkalosis, hypokalemia, and hypertension. Three limitations that my model represent one limitation is that my model doesn't show the reabsorption of sodium ions nor potassium ions, nor the membrane as well. Another limitation about my model is that it does not actually show the location of where the channel is located. Rather, I simply show the channel because the channel can typically be found in the, like I said, the renal tubules of the kidneys, and and it doesn't show the lumen that is found in the kidneys. One last limitation is that I cannot show where the actual mutation is because of the one single amino acid group. Therefore, all that is represented when the change occurs is the yellow dot, and that is it. Thank you.